Have you ever stopped to wonder how your email somehow knows what spam is? Or how your bank can flag a transaction as fraudulent, like instantly? Well, it's not magic, it's machine learning. But what I want to do today is peek under the hood and really understand how these models actually think.
Because really, it all boils down to this one question. Every single time a computer makes a prediction, it's placing an educated bet based on all the data it's seen before. Our job, then, is to teach it how to make the smartest bet it possibly can.
But here's the thing. It turns out there isn't just one right way to do this. In fact, you could say there are two fundamentally different philosophies for how to even approach a prediction problem.
So in one corner, we've got an approach that thinks in clear, logical steps, almost like a giant flowchart. And in the other corner, we have an approach that thinks entirely in probabilities, just constantly playing the odds. So let's meet our two main contenders, decision trees and naive Bayes.
First up, we're going to dive into the world of decision trees. And honestly, this one is super intuitive. If you've ever played a game of Guess Who, you already get the basic idea. It's all about asking a series of smart questions to narrow down all the possibilities.
A decision tree works by just splitting the data over and over again. And with every single question it asks, the goal is to make the groups that come out of that split more homogeneous or pure. Think of it as trying to get all the red M&Ms in one bowl and all the blue ones in another.
And how does it know if a split is any good? Well, it measures the purity with a metric, and a common one is called Gini impurity. Now, don't let the name scare you. Just think of it as a messiness score. At every single step, the tree is programmed to ask the one question that will cause that messiness score to drop the most. If a score hits 0, that means perfect purity. Game over for that branch.
Okay, but even within this world of decision trees, there are these competing ideas on how to best build one, and we can understand them with this really great analogy, the sculptor versus the cautious gardener.
So the sculptor, which represents an algorithm called CART, it just goes for it. It grows this huge, super detailed tree first, capturing every little quirk in the data. Then, it goes back and carefully chisels away all the branches that don't actually help it predict anything. The gardener, Chade, is the total opposite. It's cautious. It will not even let a new branch grow unless the statistical test first proves that it's actually going to be useful.
They also ask questions in different ways. The sculptor, Cart, only ever asks simple yes-no questions. These are called binary splits. But the gardener, Chade, is a bit more flexible. It can take one variable, like region, and create 4 branches all at once, one for north, south, east, and west. And this usually gives you trees that are a lot wider and shorter.
So what's the bottom line here? Well, CART is an absolute prediction powerhouse. It's amazing at finding really complex, subtle patterns. Chade, on the other hand, with its shorter, wider trees, is fantastic for interpretation. It's just much, much easier to read and explain to, say, a business team. It really is just different tools for different jobs.
All right, now let's completely switch gears. I want you to forget everything about flowcharts because we're entering the world of pure probability with a model called naive Bayes. It's powerful, it's incredibly fast, and it's all built on one giant and glaringly wrong assumption.
And here it is, the naive assumption. This model assumes that every single piece of evidence is completely independent of all the others. So for a spam filter, this means the word Prince has absolutely no relationship to the word Nigerian. Now, we know that's obviously wrong, right? But making this boldly incorrect assumption is exactly what makes the math simple and the model ridiculously fast.
This quote just illustrates the idea perfectly. To naive Bayes, an email isn't a sentence with structure and meaning. It's just a jumbled bag of words. The phrases "dear friend" and "friend dear" are seen as exactly the same thing. All that matters is which words are in the bag, not their order or context.
But this super simple approach has a potentially catastrophic flaw. What happens when the model is looking at a new email and it comes across a word it has never, ever seen before during its training? Well, the probability of that word showing up in spam is calculated as 0.
And since naive Bayes calculates its final score by multiplying all the word probabilities together, what happens when you multiply anything by 0? The entire calculation becomes 0. The whole thing. One single new word can completely break the model and make the prediction totally fail.
Thankfully, the fix is just beautifully simple. It's called Laplace smoothing. And you essentially just pretend you've seen every possible word one more time than you actually have, by just adding 1 to every single count, You guarantee that no probability can ever be zero. It's a simple trick that makes the model robust and prevents one new word from crashing the whole system.
So we have these two completely different models. One's a flowchart, the other is a probability machine. But it turns out they both face the exact same incredibly dangerous villain, overfitting.
Overfitting is what happens when a model gets a little too obsessed with the data it was trained on. It doesn't just learn the general pattern, it literally memorizes every random quirk and every little bit of noise. So it might look perfect on that training data, but the second you show it something new from the real world, it's a complete and utter disaster, because it never learned how to generalize.
So, a data scientist's job isn't just about building an accurate model. It's really about managing this fundamental balancing act, a constant struggle between a model that's too simple and one that's way too complex.
And this is what we call the bias-variance trade-off. Bias is the error you get from a model that's too simple. It misses the real pattern. That's underfitting. Variance, on the other hand, is the error you get from a model that's too complex and jumpy. It memorizes all the noise, and that's overfitting. Here's the catch. You can't eliminate both. As you decrease one, the other one is going to go up. The whole game is about finding that perfect sweet spot right in the middle.
So how do you find that sweet spot? How do you actually fight back against the villain of overfitting? Well, luckily, data scientists have a pretty powerful toolkit they can use.
One tool is called parameter tuning. So for a decision tree, this could mean telling the model, hey, you can't create a final rule that's based on fewer than, say, 20 people. This stops it from inventing rules based on tiny, random groups. But the most important tool, by far, is something called cross-validation. It's the ultimate reality check.
People often call cross-validation the single most important technique we have, and here's why. You chop your data up into a few pieces. You then train the model on most of them, but you hold one piece back. Then you test the model on that one piece it's never seen. And you just repeat this process until every single piece has had a turn being the test chunk. By averaging all those scores, you get a much more honest, reliable measure of how your model will actually perform out in the wild.
So we've seen two totally different ways a computer can think to try and predict the future. The logical, step-by-step flowchart on one hand, and the flexible, probability-driven bet on the other. This leaves us with a final thought, really. When you face a complex problem in your own life, which approach do you naturally lean on? Do you try to build a structured plan, or do you just play the odds?